Okay, let's start. So welcome to the last session of the blockchain course. Today we're going to talk about escrows again, and this is the last session. So please take part in the student feedback questionnaires on Canvas. I really need you to fill out that form. It takes 2 minutes. Just fill it out. We need it. Okay, so let me just share my screen. So today we're going to again talk about escrow, but before that, I want to really emphasize this point that we've seen before, that smart contracts are games. And what do I mean by this? I mean that they're not just programs. These are very different from normal programs, because if you think about a normal program, you usually have an execution of this program. And this execution is usually initiated by just one person, right? So you have this program, you're running it on your own machine, you're the one who's executing it, and whatever happens as a result of that, it doesn't really affect anyone else, right? So a normal program is only going to be executed on your machine, and you're the one who's going to see the results of that program. Whereas in case of smart contracts, they are programs, but they're put on the blockchain. And as we've seen so many times before, we can have many different people interacting with the same smart contract. So you don't just have an execution of this program that is created by one person, you have an execution that is a result of interactions of many different people with the same smart contract. And of course, these people are all trying to make as much money as possible, let's say. So in that sense, we have game theoretic interactions, meaning that we have different parties, and we're going to call the parties players. And these different players are interacting with the smart contract, and what they want to achieve is to get as much payoff as possible out of the smart contract. So actually, if we look at smart contracts as games, then this brings up the concept of the different types of players that we can have in a game like this. So what kind of players can I have? And by player, I basically just mean someone who's interacting with the smart contract. Okay. So the most common type of player that we see is a rational player. And generally, our assumption throughout this course is that everyone is rational. So whenever you design your protocols, you have to assume everyone is rational. This is true for your final project as well, and also in the exam. So this is our assumption, or maybe I can just call it the default. And who's a rational player? A rational player is a player who's only interested in their own payoff. Okay, so a rational player aims to maximize their own payoff. So basically, this means that if you're rational, you care about how much money you gain or how much money you lose. You don't care what happens to the other parties in the contract. Okay? So that's the game theoretic definition of rational. But now I can also have other types of players. I can, for example, have a malicious player. And a malicious player is someone who just wants to hurt someone else. Okay? So let's actually give some names. So here, let's say I'm talking about types of players, and let's say my player name is Alice. So Alice is rational if she aims to maximize her own payoff. And she's malicious if we have a situation where Alice aims to minimize someone else's payoff. Let's say Bob's payoff. And she does this even if she loses money herself. So a malicious player doesn't care if they're going to lose their own money. What they really care about is to make sure that someone else has a lot of loss, that someone else's payoff is minimized. So we usually use malicious players when we want to model attackers. Okay. So if I have a smart contract and I want to prove that this smart contract is safe, I usually want to prove that this smart contract is safe against malicious players. So I want to say that if you take part in my smart contract as a player, no matter what the other parties do, even if all the other parties want to just hurt you and minimize your payoff, you're not going to lose money. If I can give a guarantee like that, I can say that my contract is really financially safe. You don't lose money by joining my contract. So I use malicious players to generally model attackers. But of course, again, as I said, the default behavior is that everyone is rational. And a lot of the times you can't really give any kind of security guarantee in presence of malicious players. So it's not also very realistic to assume that someone is malicious, because if I can minimize your payoff by also minimizing my own payoff, why would I really do that in the real world? It's like, this is not a very realistic situation. But again, of course, if you can give security guarantees where you can say that my smart contract is secure, even if I have malicious players, that's a better security guarantee than saying my smart contract is secure if all players are rational. But I'm going to emphasize this many more times. The default assumption for us is that everyone is rational. Okay. So this malicious thing, it's only if I want to give stronger guarantees. But then I want to also consider another type of player, and this is just for the purposes of this particular lecture. And this is what I would call a vindictive player. So a vindictive player is a player that looks for revenge. So the idea here is that we have a protocol, and as long as everyone is following the protocol, a vindictive player will play rationally. But if they see that someone else is cheating, then they would become malicious. Okay? So a vindictive player, for example, let's say if Alice is vindictive, plays like this. So Alice interacts with the protocol or with the smart contract rationally, as long as Bob is honest, as long as Bob is following some predefined protocol that they had. Okay. But then if Alice finds out that Bob is dishonest, if Alice catches Bob cheating, let's say, then she acts maliciously. So what I mean here is that Alice just interacts with the smart contract normally, and she's trying to maximize her own payoff. She's playing the game honestly. But if at some point she sees that Bob is cheating, that Bob is not following some protocol or some agreement that they had in the past, then she suddenly becomes malicious. And then she doesn't care anymore about her own payoff. She just cares about punishing Bob, about making sure that Bob's payoff is minimized. Okay. So we have these three types of players. And again, we assume the default assumption is that all the players are rational. And today what I want to show you is that actually rationality can cost you money. So I want to show you that it sometimes makes sense to just be vindictive. And actually, there are attacks that can happen. There are cases where you can lose money if you're rational, but you will not lose money if you're vindictive. Okay. And by the way, both malicious and vindictive players are also sometimes called irrational players. Okay. So there is a question in the chat. So the vindictive player only acts maliciously towards Bob if he's caught cheating? Yes. So the idea of a vindictive player is that this is a player that looks for revenge. So as long as no one is cheating, this player is just playing rationally. But if this player catches another player cheating, then this player will become malicious towards the cheater. And so basically, this is the kind of player that will always punish cheaters. Okay, so now I want to talk about a problem that we've seen many times before, and this is the problem of escrow. And specifically, I'm going to talk about the scenario where Alice wants to buy something from Bob, and this thing that she wants to buy is in the physical world. It's an off-chain thing, it's not on the blockchain. And the payment has to be done on the blockchain, okay? So Alice wants to buy a physical good from Bob. But she wants to pay on the blockchain. Now, if you remember the lecture that we had on escrow before, the main problem here is that Alice does not trust Bob, and Bob does not trust Alice. So Alice is not willing to pay before she gets the money, before she gets the good, and Bob is not willing to send the good before he gets the money. Now, what we're going to do is to write a smart contract. So this is our initial solution. And again, this is very much something we've seen before. In this session, we're just going to go much deeper. So we write a smart contract. Alice pays the smart contract. And then Bob sends the item. And then the smart contract pays Bob. Right. That's the basic thing that we want to have. So let me actually open Remix here and let's do this. So let's say I have a constructor function. By the way, this is just an empty contract. I just have a hash function here because I will use hash functions later in this lecture. So let's say I have two addresses. I have Alice and I also have Bob. Separately. And let's say that the constructor just sets Alice to this first account that I have here. And it sets Bob to the second account. Okay, I have to make this payable. So I will just have a function, let's call it deposit, which takes a deposit from Alice. Okay, so I just require that the person sending this particular message, so the person calling this function has to be Alice. And then I also require that it has some particular value X. And I'm just going to have UNT X, which is the amount that I want to pay. So let's say 1 Ether. Okay. So Alice has to deposit 1 Ether. Now, afterwards, there should be some time for Bob to actually fulfill the item. And then we have to somehow decide if both sides agree on whether the item was fulfilled or not. And we don't want to use a trusted third party. So the solution that we had was very simple. The solution we've seen before is that each one of the parties can just send one bit of information to the contract, and that bit of information says whether the item is fulfilled from their point of view, right? And then if they agree, we will pay out the deposits correctly. If they don't agree, we will not. And we saw before that it actually makes sense to also ask for a deposit from Bob, just to make sure that Bob is also incentivized to do the right thing. And basically, if we catch Bob cheating, we can somehow punish him. So if I don't take a deposit from Bob, there is no way that I can actually punish him later if he does something wrong. So we've talked about this before. I'm going to take a deposit of 2x from Alice, and x was the value of the item. And I'm going to take a deposit of x from Bob, okay? So maybe I can just have two different functions. I call one deposit Alice, and I require that the deposit comes from Alice, and its value is 2x. I will have another function called deposit Bob. This is public and payable. And again, here I require that this function can only be called by Bob. And I also require that it gives me a deposit of x. Okay. And actually, you've implemented these things before, so it makes sense to have, let's say, two Boolean values called Alice deposited, let's say, and Bob deposited, which just tell us whether Alice and Bob have made the deposits. Okay. Okay, and here I would say after I get the deposit from Alice, I set Alice deposited to true. And here I require that Alice has not deposited before. I want to only take one deposit. And here I say Bob deposited is true. And I also require that Bob can only deposit once. Okay, so in this session, we're not just talking about escrow. I'm going to also show you some of the common mistakes that I saw in a lot of submissions to the homeworks. So one of the common mistakes is if you actually let them deposit too much, then the contract will have too much money, and it might be that the money gets locked in the contract if you don't have a way for them to get the money out of the contract. And of course, another case is I want to make sure that one party can withdraw their deposits if the other party does not deposit anything. So maybe I can have a function called withdraw Alice. This is public and payable. And I basically require several things. First of all, I want to make sure that only Alice can call this. And then I want to make sure that Alice has deposited when she calls this. And I also want to make sure that Bob has not deposited. So the idea is that if you're Alice and you've made the deposit, but Bob has not made the deposit, you can withdraw. Okay. And I'm not enforcing any time limit at this point. I'm just saying at any time, as long as Bob has not yet deposited, Alice can get her deposit back. Okay. So if this case happens, I would set Alice deposited to false. And I would send Alice's money back to her. Now, how can I send money back to her? We've talked about this before again. We have three different functions. We have transfer, send, and call. And we said that we should always send money using call. So the syntax here is actually like this. I would say alice.call. And then I have to say what function I want to call. And in this case, because I expect that Alice would not be a contract. I'm just calling the null function nothing, which basically just means give the money to Alice. And the value of this call, so the amount of money that I'm going to send with this call, is going to be 2 times x. Okay, and well, a call returns 2 things. It returns a Boolean, which is basically whether the call succeeded or not, and we usually call that sent. And it also returns whatever the return value of the call was. So call it data. In this case, I don't really care about the return value of the call because I don't expect it to return anything. I'm just sending some money to Alice. But I care about this Boolean value because I want to make sure that Alice received the money. So I just say require sent. So what's happening here? This line is trying to send 2 times x, this amount of ether, to Alice. And if this succeeds, then this sent would be true, and then this require passes, and the function call goes through, and everything is fine. Otherwise, if this call fails for any reason, if I cannot send the money to Alice, sent would be false, which means that this requirement here would be false, which means that the entire function call will be reverted. And if I revert the entire function call, it also reverts the change to Alice deposited. So Alice deposited again becomes true if the function call is reverted. So this is a safe way of writing this withdrawal. Now I can of course have a simple function just like this for Bob. So a very similar function. I don't need this to be payable. So. And it's just the opposite of this. It's like I want to only let Bob send this message, and he can send this if he has deposited and Alice has not deposited. And in this case, I would set Bob deposited to false. And I'm too lazy, so let me just copy this. Send this to Bob. And the value should be x. Okay, and the warning here is that we are ignoring this data, but we're doing that on purpose. Okay, all I've written here is just the deposits, but now let's say both sides have put down a deposit. So as soon as they both put down a deposit, none of them can call withdraw now, and so everyone's money is locked. Now, I want to give Bob some amount of time to actually send the item in the real world to Alice. And let's say that this amount of time is, for example, 1,000 blocks. Okay. So let me just call it Bob's deadline or Bob's time. And this is going to be 1,000 blocks. And I'm going to also say when this starts. So I'm going to have a lock time, which is originally 0. And this lock time is going to basically be the number of the block in which everyone's money is locked. So the money is locked when both sides deposit. So here I can say if Bob deposited, then lock time becomes the current time, which is block.number. Okay, and again, I use the block numbers as my time. And here also, when Bob deposits, I say if Alice has already deposited, then the lock time becomes the current time. Okay. So now the idea is that from the lock time up until lock time plus 1,000, Bob has time to send the item to Alice. And then after this, after all of this ends, after Bob's deadline basically passes, we can have the two sides coming back to the contract and telling the contract whether they think the item was fulfilled or not. So let's call this Alice's choice and Bob's choice. Okay, these are again Booleans. So Alice's choice is true if Alice has told the contract that she thinks the item was fulfilled, and the same for Bob. So here I will just have a function. I call it declare. This is also public. And let's say that only Alice or Bob can call it. So MSG.sender should either be Alice or it should be Bob. And let's say I have a bool here, D, which is the thing that they're declaring. And I say if MSG.sender is Alice, if Alice calls this function, then Alice choice becomes D, otherwise Bob choice becomes D. Okay. Now, a very common vulnerability that I've seen in your codes is that you can write something like this, and this actually allows people to declare more than once, right? So I want to make sure that they can declare only once. So I actually need, maybe let me take this back down. No, sorry. No, let them be there. So I also need another Boolean, Alice declared, and another Boolean called Bob declared. And I need this because I want to make sure that Alice and Bob can declare only once. Okay. So here I want to say after Alice declares, I set Alice's choice, but Alice declared also becomes true. And here I want to do the same thing for Bob. I want to say Bob declared is true. Okay, and I want to make sure that they cannot declare more than once. So my requirement would be that I require that the function caller is Alice and Alice has not declared before, or that the function is called by Bob. And Bob has not declared. Okay, this makes sure they can have only one declaration, but I also want to say that they can only declare after the deadline for Bob has passed. So I'm going to require that the current block number is more than the lock time plus the amount of time that Bob had, so let's call this Bob time, to send the item. Okay. Block.number should be more than lock time plus Bob. I still have a bug. What's the bug here? The bug is that the lock time is originally set to 0, right? So I have a situation where none of the parties have deposited, so no money is really locked. And despite the fact that no money is locked, someone is calling declare. So I have to check for that as well. I have to require that Alice deposited and Bob deposited, because otherwise it's not even locked. So this one makes sure that both parties have deposited. This one makes sure that 1,000 blocks have passed since the last deposit. This one makes sure that only the two parties can call this function and each party can declare only once. And finally, this one updates the choices. Okay. Nice. So finally, I'm going to have another function. And this function is going to basically pay everyone back. Now, a very important thing is the point that I've put on canvas, and this is called pull over push. So you never want to have a situation where you have a function that is called by one person and sends money to another person. So why do I say that? So let me go back here. Just for a second, this is a detour. let's say that function f is called by Alice, but pays Bob. Now, what are the options that I have in my function f for paying Bob? I can use either transfer or send or call, okay? So I have one of these three cases. Either I have Bob.transfer some amount in my function, or I have Bob.send some amount in my function, or I have Bob.call. Okay, and in this case, the value of the call is the amount that I want to send. Okay. So I have one of these three ways to send money to Bob. Now let's see what the problems are with each of these. If I use Bob.transfer, I have a gas problem. And the problem is that transfer only sends, okay, I think it was 2,300 units of gas. So transfer and send, they both allocate very little gas. So if Bob is a contract that receives this money, the receive function of Bob will be called, and then there might not be enough gas. So the problem that I have with both transfer and send is that I might not have enough gas. Okay, and here again, I have not enough gas. And this is especially the case if Bob is a contract. And let's say when Bob receives this money in the receive function or in the fallback function, Bob might want to do some accounting. Maybe Bob wants to update some variables in his own contract to make sure he's keeping track of what money was paid and where the money came from and things like that. So there would not be enough gas for this. But we have another problem with transfer, and the problem is that we've seen this before. Transfer calls the receive function of Bob, and then Bob can actually throw an exception in its receive function. So Bob's receive function, or actually even the fallback function, it can be either, can revert, can throw an exception, and that would revert the execution. And it will not only revert the transfer, it will also revert F. And if that happens, that means that Alice basically cannot call F unless Bob allows her to, because every time that Alice calls F, maybe Bob's code in receive or fallback just reverts it. And if that happens, that basically means Alice cannot call F, right? So Bob can disable some functionality for Alice. Now let's see what happens if we use send. So let's say function F is a function in your smart contract that is supposed to be called by Alice, but it's going to pay Bob. And let's say I use send. Again, I have the same problem that maybe I don't have enough gas because send calls Bob's receive or fallback function. So I might not have enough gas. I don't have this second problem because if Bob's receive or fallback function reverts, in case of send, it only reverts the send. So it sends the money back, but the execution of F continues. F is not reverted, okay? So in this case, F cannot be reverted by Bob. But this creates a different problem. Let's say that Bob really wasn't malicious, but really needed to revert. Maybe Bob had an exception. Maybe Bob's contract had a bug. Something happened. I don't know. Or maybe Bob needed more gas. So there might be many cases where this send fails. And if the send fails, the execution of F just continues. So it might be that in your function F, you're assuming that you have paid Bob, but Bob hasn't actually received anything. So that's also problematic. Okay, so we saw that we cannot use transfer, we cannot use send because both of them create different problems. Now let's say I use call. What happens if I use call? Call doesn't have any of these problems, right? Because I can say exactly what the value is, and I can also share my gas with Bob. Well, the problem here is that if Bob is a malicious contract, Bob can actually use up all of the gas. Okay, so Bob can intentionally waste gas. Okay, how does this work? Let me just show you a very simple example here. So let's say I have a contract, and this is a vulnerable contract, so I'm just going to call it vulnerable. I have a function f, let's say it's public and payable, and let's say it can only be called by Alice, so I require msg.sender to be Alice, so Alice was this one. Okay, and yeah, let me just write Alice, just copy Alice and Bob from up here. I have Alice, I have Bob, and I have my constructor, which basically gives them their values. And let's say I also have a receive function, or maybe I have a function called deposit, which is public and payable. And, or actually, no, let me just do it with one function, sorry. So I'm writing a vulnerable contract. I have Alice and Bob, and I have this function f, and Alice can pay some money. And let's say I require that this function f is called by Alice. Okay, whatever. Let's say I also have a function called deposits, which is public and payable. So anyone can send money to this contract. I could also just call it receive, but let's say I have this function f now that can only be called by Alice. And let's say that f wants to pay Bob using a call. Okay, so I'm just going to say, maybe I want to send all the money in this contract to Bob. Or maybe I want to say send half of the money to Bob and half of the money to Alice. So I just say bob.call, and the value that I'm going to send to Bob is going to be the balance of the current contract. So address this balance, but only half of it. Okay, so I send half of the money to Bob, and then I send the remaining money to Alice. Okay, this looks perfectly fine, right? It looks like if it fails, it's Bob's fault because, well, Bob's call failed. And everything kind of looks nice. But now here's the attack that Bob can do. If Bob was not just an address of a real person, of an externally owned account, if Bob was actually a contract, Bob could do this. So let's say I have a contract. I'm going to call this attacker Bob. Now, this contract is going to have a receive function, right? And, or maybe let me just write the fallback function instead of the receive function. So it's going to have a fallback function, which is called whenever someone sends money. So here, when I'm sending this money to Bob, I'm calling Bob's fallback function. Now, here's what Bob can do. Bob can say, as long as the amount of gas that is left is more than some tiny amount, okay, as long as it's more than, let's say, 1,000. Just do some ridiculous calculation. Just do something that wastes gas. So just do this. Okay. So Bob's attack here is to just waste a lot of gas. Now, what happens when Alice calls the function f? Let's say Alice calls f. She wants to get half of the money, and Bob also is supposed to get half of the money. So this money is sent to Bob, but then Bob's fallback function is called, and Bob's fallback function wastes all the gas. And then when this fallback function ends, you have less than 1,000 units of gas. This 1,000, it was just a number that I made up. You can change it according to your attack. So let's say after this call ends, you have very little gas left. So when the call to Alice happens, there is not enough gas to make that call. So the function f will get reverted. So basically that means that Bob can make sure that this function f always runs out of gas, no matter how much gas you've allocated for it when you called it, which is equivalent to saying that Bob can make sure that Alice can never call this function f. Okay, so any call to this function f would just be a waste of gas. Okay, so now that we're seeing this attack, we know that even call is vulnerable. So what can we do? Well, when we're doing the call, we can actually also set the amount of gas. So I can say that give these many units of gas, maybe give 10,000 units of gas for this call. So this will avoid this particular attack. But a much better thing to do, okay, so this avoids this attack, but then it opens up the previous problem, right? What happens if Bob actually is not malicious, but he needs more gas for his receive or fallback function for some reason? He needs to do some calculation. So all of these cases are actually quite nasty. So the best thing we can do is to make sure that we always have a pull over push situation, which means that instead of pushing money to Bob, we always ask Bob to pull his own money out. So whenever a function is called, we add the extra requirements that we would only pay the person who has called this function. Because if this function f was called by Bob and not by Alice, then we wouldn't have any of these problems. Bob would not intentionally waste gas because he's the one who's paid for the gas, right? And he would also not revert it because, again, he's the one who's paying for gas. Why would you create a transaction that would just be reverted? Right, so all of these attacks will go away if you just make sure that whenever someone calls a function, that function can only pay the caller. Okay, so let me now just delete all of this and go back to my escrow. So after both parties have declared their choice, I will have a function which is like get money back, let's say. I can call it whatever. And this is also public. And I say this function has to be called by either Alice or Bob. So require msg.sender to be Alice or msg.sender to be Bob. I want to make sure no one else can call it. I want to make sure that both people have declared before I call this get money back. So I'm going to require Alice declared and Bob declared. So you can get your money back only after both parties have declared. Or actually, and maybe call it get payoff. And yeah, so now I'm going to have two more booleans. So I'm going to say whether Bob is paid and whether Alice is paid, because I don't want to pay someone more than once. So in the first case, I say if this function was called by Alice, you have to pay Alice, else, so if sender was Alice, otherwise, if it was called by Bob, you have to pay Bob. Now, how much do I have to pay to Alice? So we've seen this before. There are several different cases. The first case is that the two parties do not agree with each other. So if the two parties do not agree with each other, so if Bob's choice and Alice's choice are not the same, the payoff has to be 0. So let's say I have payoff here, and this payoff becomes 0. Otherwise, if they actually agree, if Bob's choice is 1 and Alice's choice is also 1, this means that they both agree that the item was fulfilled. So remember, Alice at the beginning put 2x units of deposit. X units of that should go to Bob, and the other X units should go back to Alice. So I would say the payoff to Alice would be X in this case. Otherwise, if they both agree that if they both agree that the item was not fulfilled, so if both of their choices are 0, then Alice should get a complete refund of her money. So the payoff is going to be 2x. Now I can similarly compute a payoff for Bob. So in this case, I'm going to say again, if they don't agree, the payoff is 0. His money is going to be burned, locked in the contract forever. If they both agree that the item was fulfilled, Bob should get 2x because he put a deposit of x, and he should also get x from Alice. And if they both agree that the item was not fulfilled, Bob should just get his own deposit x back. Okay. Yeah, and actually I can't write 0 and 1. I have to write true and false. Okay, finally, I have to pay this payoff to Alice in this case and to Bob in that case. So again, I say alice.call, and the value is going to be the payoff that I just calculated, and I'm not calling any function. I'm just calling the fallback function or receive function of Alice. And I will also have situation like before. And I'm going to say require set. Okay. So this means that if Alice calls this function, I will pay Alice, but I will also check that the payment was successful. And if the payment was not successful, I will just revert the transaction, which means everything goes back to the situation before this function was called. It's as if this function was never called. Okay, but I have to also make sure that I update Alice paid. So here I'm going to say, okay, good point. If MSG.sender is Alice, I have to add a requirement that Alice was not paid before. Okay. And if the person calling this was Bob, I have to make sure that Bob was not paid before. Now, when should I update this flag that says Alice was paid? Okay. So one mistake is this. If I do it like this, then I would be vulnerable to reentrancy, right? Because let's say Alice calls get payoff, and this function comes here, calculates the payoff, sends the money to Alice. But when it sends the money to Alice, this call is going to call the receive function, or actually, sorry, the fallback function of Alice. And then Alice's fallback function can make another call to get payoff. And that call will be executed before Alice paid is set to true. So to make sure I don't have reentrancy, I have to put this before sending it. So Alice paid is first true, so that if I have reentrancy, if this call comes back and calls get payoff again, it will not satisfy this requirement here. So now I'm safe against reentrancy. And I have to do the exact same thing here. I say Bob paid is true. And I'm going to do the exact same thing, except that I'm going to pay Bob. Okay, great. Now, why is this better than other ways of sending money? Generally because, well, I don't have any limitation on call here. This call can use as much gas as it wants, but actually the person who's paying for that gas is Alice. So I'm making a call to Alice only when Alice is the one who's calling this function get payoff. So Alice is the one who's paying for the gas. So I don't care how much gas it uses because Alice is paying for it. Alice had the choice. She knows what she's doing. And the same thing here for Bob. So whenever a function is called by one person, I want only that person to be paid. Okay. We have a question in the chat. What if the contract ensures Alice and Bob will not be a contract? Will the pullover push become unnecessary? Yes. So if you're sure that Alice and Bob are not contracts, you can just always use transfer. And none of those attacks will exist. But that's generally not a good practice because normally we want to have contracts that can interact with other contracts. So yeah, of course, I could just make sure that Alice and Bob are not contracts. And the way you can do that is that you can have a sign up function where Alice and Bob sign up to your contract. And then you can have something like this in that function. You can have require msg.sender equals tx.origin, because tx.origin is never a contract. tx.origin is the originator of the transaction, the person who's created the transaction. It has to be an external account. And if you do this, you are guaranteed that you're not working with contracts and you don't have any of these vulnerabilities. But I generally do not really suggest this because it just limits the functionality of your contract. And most people don't want to just directly work with your contract. Maybe they want to make function calls through other contracts. So don't do this. Just write your contract in a safe way. Just do pull over push. Okay, but yeah, all of this was a detour. Let's get back to our main topic here. So I have this I fixed this. Now I have a solution where I had a smart contract. Both parties paid the smart contract. It wasn't actually just Alice, but also Bob who sent a deposit to the smart contract. And then they both told the smart contract what their choice is going to be. And then based on that choice, the smart contract is paying. Now, the problem I have here, and again, we've seen even this one before, is an extortion attack. Okay, what is the extortion attack? So suppose that Bob is dishonest. Okay, so if Bob is dishonest, what can he do? So first of all, he signs up. So Bob pays his deposit of 2x. And let's say Alice pays it as well, and the money is locked. In the next step, Bob does not send the item. Instead, he just waits for 1,000 blocks. So waits for exactly 1,000 blocks, not even more. So remember, he had 1,000 blocks time to send the item. So he just waits for 1,000 blocks. And then he declares that he has sent the item. So he just calls declare true. Okay. Now, if he does this, What happens from the point of view of Alice? So Alice knows that the item was not actually fulfilled, but Alice can also see the blockchain. So Alice sees that Bob has declared true. So now Alice has two choices. Either she declares false or she declares true. And the honest thing to do is to declare false because, well, the item was not fulfilled. But let's look at this thing here. Let's look at Alice's payoff. So Bob has declared true. If Alice declares false, we will be in this case, and no money will be paid back to Alice. But if Alice declares true, we will be in this case, and actually X units will be paid back to Alice. So we go back to this definition here. If Alice is rational, she would be extorted. If Alice is rational, she would declare true. Because even though Bob is basically stealing money from her, her choices are between declaring true or false. And if she declares false, she will have a lower payoff than if she declares true. So a rational Alice in this situation will be extorted and would declare true. But now what happens if Alice is vindictive? If Alice is vindictive, she says, I don't care that I'm going to lose money. Bob has cheated now because I know the item was not fulfilled, but Bob has declared true. So I'm not going to look at my own payoff at all. I'm going to just look at Bob's payoff and I'm going to figure out how to hurt Bob as much as possible, how to take revenge on Bob. Okay, so Bob has declared true. So Alice knows that if she declares true as well, Bob will be paid 2x. But she knows that if she declares false, we will be in this case and Bob will be paid 0. So Bob will lose that 2x. So a vindictive Alice in this case would declare false. And so the attack doesn't work on a vindictive person. The extortion attack, it only works if Alice is rational. If Alice is vindictive, this attack will just lose Bob a lot of money. And again, we're assuming Bob is rational. So let's say Bob is rational. If both parties are rational, if Bob is rational and Alice is also rational, then Alice can be extorted. But if Bob is rational but Alice is vindictive, then Alice cannot be extorted. But of course, it's really up to psychology to decide whether you think people are rational or vindictive in the real world. Again, the default assumption is always that everyone is rational. So in this case, Alice will be extorted. Okay, how can we fix this? Let's have an extension of our contract in which, let's say we have some sort of a commitment scheme. So let's say that instead of just giving their choices out, instead of just having this function declare, they actually declare the hash of their choices. So let me have something called declare hash. Okay. And instead of just giving a Boolean, let's say that they give a uint. And I'm going to call this H, which is supposed to be the hash of their choice. And so here I'm just going to say Alice, instead of choice, let's call it hash. Alice hash becomes H. And here I'm going to say Bob hash becomes H. Okay, oh, sorry, it should be bytes 32. So here, other than choice, I will have bytes 32 called Alice hash and another bytes 32 called Bob hash. Okay. And then I also need to reveal, and so I need to have some Booleans. So I will have a Boolean called Alice revealed and another Boolean called Bob revealed. And then here I will have another function for revealing. So I will have function reveal, which is public and takes some integer x. And then I say that I require this function to only be called by either Alice or Bob. So msg.sender is either Alice or Bob. Of course, you can just write a modifier for all of these things so that you don't have to write them again. I would also want to require that both of them have already declared. So require Alice declared and Bob declared. And then I want to require that the hash of this thing, so I had a hash function up there. I want to require that the hash of X is, well, so I want to say if msg.sender is Alice, I want to require that the hash of X is actually Alice's hash. And then I would say Alice's choice. I just say if X is odd, Alice's choice is true. Otherwise, Alice's choice is false. Does that make sense? So this X is basically the choice and the nonce combined. It's just a large number, and if it's its last digit, its last binary digit is the choice. Okay. Of course, I want to make sure that they cannot reveal more than once. So I would say require not Alice revealed, and here I would say Alice revealed is true. And then the same thing for Bob. So if Bob sends the message, I require that Bob has not revealed. I require that the hash of X is Bob's hash. And in this case, Bob's choice would be 1. In this case, Bob's choice would be 0. And so on. Of course, you also need to write another function that people can actually use to get back their money in case the other side does not reveal. So you have to make sure that money never gets locked in your contract. I'm not going to write that right now, but it's just an easy thing to write. So you can just write that if after a given time Alice has revealed, but Bob has not revealed, then Alice can get all the money of the contract. And the same thing for Bob. So if after a given time Bob has revealed, but Alice has not revealed, then Bob can get all the money in the contract, so that we make sure that both sides reveal. Okay. So I'm not going to write that part. We don't really have time for that, but like in your final project and so on, we expect all of these things to be handled correctly. We expect you to make sure no money gets locked in your contract unless that's the desired behavior. Okay. So now I have a situation like this. But does this change anything? Does this make it so that Bob cannot extort Alice? So remember, Bob is dishonest. He can't just declare true. But here's what he can do. He declares some hash, right? So he declares the hash of true and some nonce. Right? And Alice cannot know what Bob has declared. Alice does not know if Bob has committed to true or to false because Alice doesn't know the nonce. But here's the thing. In this case, Bob is the attacker. Bob wants Alice to know. Bob wants Alice to know that he has declared true. So he just sends a message to Alice. So Bob sends his nonce to Alice. In this case, it was called X or, yeah. So Bob sends his X, which is like true and the nonce, to Alice. And this is again enough for extortion. Because Alice can see the blockchain, so Alice can see what was the hash that Bob committed to. And now Bob has given Alice the nonce, so Alice can check that Bob actually committed to true. And that means that Alice knows that Bob's choice is true. And then we have the same game theoretic analysis as before. If Alice is rational, she's going to be extorted because she's going to also declare true. And if Alice is vindictive, she's not going to be extorted because she's going to punish Bob. But let's just assume Alice is rational. If Alice is rational, she will be extorted here. So as we see here, this idea of adding a commitment scheme, it doesn't really help. It doesn't change anything, because the whole point of the commitment scheme is to hide data, but in this case, the person who knows the data, who's Bob, is intentionally leaking the data. So he can just leak the data to Alice, and this leak is what makes it possible for Bob to extort Alice. Okay, but here's the next step. Let's say I want to defend against this. How can I defend against this? I can say, if Alice can guess Bob's value X, then I would pay all the money in the contract to Alice. Okay. So maybe I can have some timers. I can say, you have a particular amount of time to commit. Everyone has to commit in that timeline. And then you will have another time segment after that to reveal. And everyone should reveal in the second time segment. Now I say, in the first time segment, in the time for committing, if Alice can tell me what was the value that Bob committed to, so that makes sure that that basically proves to the contract that Bob was leaking. So if Alice reports this value of X to the contract can actually check this value, because the contract can just take the hash and see that this was the hash that Bob had declared. And then the contract can punish Bob, right? And I can have the same thing on the other side as well. So we call this unmasking. If Alice can unmask Bob, if Alice can show the value that Bob has committed to, if Alice can show Bob's nonce to the contract before the time for revealing, then the contract knows that Bob was trying to extort Alice, so it can pay all the money to Alice. Now, it seems like this solves the problem, but it doesn't solve the problem. Now, why doesn't it solve the problem? Because maybe Bob gives Alice a zero knowledge proof. Remember, so in the past 2 sessions, we talked about zero knowledge proofs. It might be that Bob declares true. So he just submits the hash of this value X, which corresponds to true and a nonce to the contract. But instead of giving this X to Alice, he gives a zero knowledge proof that such an X exists. And if he gives a proof like that to Alice, then Alice is convinced that Bob has declared true, but Alice cannot prove it to the contract, because remember, the whole point of a zero knowledge proof was that you don't leak any extra information, right? So Bob convinces Alice that he has declared true. That's the thing that he gives a zero knowledge proof for. But Alice cannot convince the contract that Bob has declared true, because zero knowledge proofs were not convincing to others. Remember, that was actually one of the cases we talked about. Like, if Alice and Bob prove something between themselves, they can't, the verifier cannot take the proof and replay it for someone else to convince them. So in this case, again, the contract remains vulnerable, because Bob can just give a zero knowledge proof to Alice. But we have an even nicer attack, something that doesn't even use zero knowledge proofs. And this is basically called the rationality attack, or the side contract attack. So here's the thing. Let's look at this contract. And let's say I've implemented this extra functionality that if Alice can unmask Bob, then Bob will be punished. So Bob makes sure that he will not reveal his value of X to Alice before the time to reveal comes in this contract. And let's say I have timelines. So for each one of the functions, I have a requirement that it has to be called between this block number and this block number, okay? So if I make those changes, then Bob has declared the hash H, right? He wants to prove to Alice that this hash H actually corresponds to the choice of true, corresponds to the case where Bob is saying the item was fulfilled. But he does not want to leak the value X, whose hash is this value H. So how can he do this? here's how we can do it, and I'm going to just write it up here. I'm going to call this side contract attack. So Bob is going to create another contract. Now, what does this other contract do? First of all, it has the same hash function as the original contract. Secondly, it has a deposit function, which is public and payable. Okay. And let's say that it also knows the address of Bob. And yeah, this is my constructor. I don't care about Alice at this point. I just want to have Bob. Okay. And then I also have a function called withdraw. And this is public, and it's also payable. Oh, well, no, it's not payable. Let's say I just have a function called withdraw, which is public. Anyone can call it, but it only pays Bob. And what this function does is that it just sends the entirety of the balance of this contract to Bob. And let's say Bob is not a contract, so let's say I can use transfer. Again, I just don't have time, otherwise I have to use call here. We're running out of time, so I'm going to write vulnerable code here. I want you to just see the main idea here. So consider this very simple contract. It's a contract that can receive money from anyone, and it will just pay that money to Bob whenever someone calls withdraw. And yeah, I can even say that I require msg.sender to be Bob. So anyone can give money to this contract, and only Bob can take money out. Okay, let me do it with call. Bob.call value is this. Calling nothing. I don't even need to check it, because if the call fails, you can just call withdraw again. Who cares? Okay. So it's a very simple contract. But now I'm going to do this. I'm going to put H here. I'm going to say there is a value of H. And I'm going to set this value of H in the constructor. So H is something. Okay. And here, I'm going to say, in order to withdraw, you need to give me a number X. And I'm going to require that the hash of X is H. And I'm also going to require that X is an odd number, which corresponded to X being the true choice. Okay, so what is this contract? This is an attack contract that Bob writes, and he publishes this contract on the blockchain. And then he deposits some large amount of money here. He deposits maybe 10 times the amount of money that is at stake in the other contract between him and Alex. Okay, now what is this contract saying? And this H here is going to be the hash value that Bob has actually used here when he was declaring his hash. So it's Bob's hash, basically. It was easier to call it Bob hash. I don't know why I called it H. Okay, let's call it Bob hash. So I have this Bob hash here. I set the value in the constructor, and I reverse. So what Bob is doing here is that he's creating another contract, and he's putting some of his money in this other contract. But this contract gives the money back to Bob if and only if his choice in the original contract was true. So the only case that Bob can get his money back from this side contract is if his hash in the original contract was hash of a number X, such that that number X was a choice that said, I've fulfilled the item. Okay. So basically, the way Bob is proving to Alice that he has said to the contract that he's fulfilled the item is very simple. He's saying, I'm going to punish myself if I've said anything else. I'm going to create this other contract and I'm going to, let's say, pay it 10 Ether. And this escrow was over 1 Ether. So I'm going to create this other side contract. I'm going to pay it 10 Ether. And I've written this side contract in a way that it gives me my 10 Ether back if and only if I can give it a value of X that hashes to the hash that I have in our escrow contract. And if that value of X corresponds to a case where I declared that I've given you the item. So my choice was true. Okay. So why does this work? This works because Alice understands now that since Bob is rational, Bob would never write such a contract and put money in it if he could not get his money back. And the fact that Bob is rational and he would need to get his money back proves to Alice that Bob actually committed to the true choice in the original contract. Proves to Alice that Bob is actually saying that he has fulfilled the item, and that's all we needed for the extortion. So now Alice knows nothing about the hash that was submitted by Bob. So, sorry, Alice knows the hash that was submitted by Bob, but she doesn't know the nonce that was submitted by Bob. The only thing she knows is that Bob has created another contract in which if Bob cannot give a nonce, which corresponds to true, and when hashed gives the hash that he declared in the original contract, if he cannot do this, he will lose a lot of money. And because of this, Alice is convinced that Bob actually knows a value X, which is like true and some nonce and has that particular hash. And this proves to Alice that Bob has actually declared that he has fulfilled the item. And then we get back to the game theoretic analysis again. We are again at the same point where we have a situation like this. If Alice is rational, it's proven to Alice now that Bob's choice was true, so she can either choose to play true or false. If she plays true, she gets a higher payoff than if she plays false. So a rational Alice would play true, which means that a rational Alice will be extorted. A rational Alice put a deposit of 2x in here, but she's only getting back a payoff of x, and she's not getting her item from Bob. Okay. Now, the part that makes things even more interesting is that it can actually be proven that there is no way around this. So no matter how you write your escrow contract, I can write a side contract like this that would actually make sure a rational Alice would be extorted. So if we assume that Alice is rational, it doesn't matter how I'm implementing my escrow. It doesn't matter if I'm using commitment schemes or I'm using any kind of other fancy cryptography. No matter what I do, Bob can always write a contract like this. Of course, if my original contract is more complicated, then this contract will also become more complicated. But Bob can always write a side contract in which she proves to Alice that in the original contract, I'm going to be dishonest. And if I'm not dishonest in the original contract, I will be punished in this side contract. And this proof makes it so that Alice is forced to be extorted and basically accept that she has received the item, even though she hasn't. But again, going back to the point that I raised at the beginning of this lecture, and this is the point on which I want to end this entire course, is that it's actually good to be vindictive. It's good to take revenge. So if Alice were vindictive, none of this would happen. If Alice was definitely someone who would punish Bob for any kind of cheating, if Bob could count on the fact that Alice is not rational, that Alice is not just aiming to maximize her own payoff, she actually cares about truth and she will punish Bob if Bob cheats, then Bob cannot do any kind of attack like this at all. So the entire point of this lecture was that if you're rational, you can be extorted. If you're not rational, if you're vindictive, you cannot be extorted. So if you're interacting with smart contracts, be vindictive. And of course, it comes with a cost, right? So the cost of being vindictive is that sometimes you have to actually lose some money. But being vindictive pays off in the long term. Like if everyone knows you're vindictive, they will never try to do these kinds of attacks. Okay, great. So I'll see you at the final exam. And this is the end of the course. If you have any questions, you can ask in the chat and I will answer them. Otherwise, see you, I think, on the 25th at the final exam. And take part in the student feedback questionnaires. Again, student feedback questionnaires are important.